Welcome, ladies and gentlemen, to another exciting episode of Dave Does Math from Home. Today we are talking about section 15.3. We have had our section on what multivariable functions are and what they look like and how they behave. We've had our section on what multivariable limits look like and what they mean and how they behave. So it's time to go directly into derivatives. And this is how we go into derivatives. The section is called partial derivatives, and I'll see if I can explain that name first. In two dimensions, when we take a derivative, the idea of derivative is connected to the idea of a slope. So the information that you get from this derivative idea, this derivative number, that information means as x moves from left to right, what does y do? Let's do it without my back to you. As x moves from left to right, what is y doing? Is y decreasing? Is y increasing? How fast is it increasing? And we can get away with that because x moving from left to right is basically the only thing that's happening in the independent variable. X increases. It's pretty straightforward on that count. When we do derivatives in multivariable situations, we're going to kind of run into sort of the same problem we ran into with limits. When we did limits, two-dimensional limits have to agree from both directions because there are exactly two directions, and that's it. When we do limits in 3 dimensions, you have to consider all of the different paths that might lead to that point and what the limit is doing in all these different paths. And we're going to have the same problem with derivatives. It's not just about x increasing anymore. X is going to change, and y is going to change, and they're going to change completely independently of one another. That's what it means that they are independent variables. They don't depend on each other or anything else. They're just going to do what they want to do. And that means that we have to account for how they're going to change, or rather, when they change, how is z going to change with them? So there is no like whole singular entire derivative. We can only ever do derivatives for 3-dimensional functions in pieces, which is why they're called partial derivatives. So the pieces we're going to break this up into are what happens as x changes, what happens as y changes, and that's about it. So if we're still going to go on this being the classic x and y and z being coming out, some surface that comes out of the board at us or is behind the board farther away from us, then we're going to look at what happens in this direction. As x moves this way, does this surface increase or does it decrease or does it wiggle? Like what's going on as we move exclusively in this direction? And the thing about moving exclusively in this direction is that y is not going to change at all. If you pick this thing and you go that way, there's no change in y. Y along this path is effectively a constant. And that's the good news. We can treat it like it's a constant when we're doing derivatives along the x direction. And then separately from that, we're going to do derivatives along the y direction. As y increases, does this function increase? Does it decrease? Does it wiggle? Does it stay the same? And again, when we're moving along this path, x isn't changing. X is this fixed value the whole time we go along this path. So when we do derivatives with respect to y, we can treat x like it's a constant. And that's the entire idea of partial derivatives. You figure out what variable you're differentiating with respect to. You pretend like all the other variables involved are constant, because they are, except for the dependent variable. Hopefully that's going to change when you change whatever variable you're differentiating with respect to. And you look at how your dependent variable, your z, usually, will change as x changes, and then separately as y changes. That's the basic idea. Let's get into it with some examples so you can see, hopefully, what I'm talking about. Let's see if we can pick an example where we try to establish some graphical interpretations of this as well. Let's say 12 minus 6x minus 2y. We've seen something like this before. We know that this is a plane, and that if we graph what is happening on this plane in only the first octant, we get a kind of a triangle shaped thing. So z is going to be up here at 12. There's that intercept. We'll make this x and this y. The x intercept is going to happen at 2. When x is 2, that's what makes these other things 0. And the y-intercept is going to happen at 6. So you'll have a slope that kind of looks like this, or a plane that looks like this. So let's find the derivative of z with respect to x. I'm bad at writing this letter, but this is supposed to be a fancy script D. And the fancy script D means it's a partial derivative instead of a normal derivative. I just am bad at distinguishing the fancy script D from the regular D. Hopefully, when you see it typeset on the homework, hopefully it will be very clear. But all the D's in this place are going to be very fancy and scripty. Sort of like an italicized D, maybe. So this is how we're going to write it. Hopefully you remember this is Leibniz's notation. Leibniz described his derivatives using D's. Newton used little primes. Primes are not going to work for us at all anymore in any capacity, because the prime just means derivative. It doesn't tell us what we're differentiating with respect to. And since we absolutely must know in this context which variable we're differentiating with respect to, Newton's notation is right out. Cannot use it. It is not going to help us at all. So this is dz dx. It's the derivative of z with respect to x. When we take this derivative, all the derivative rules still apply. We just get to pretend like anything that's not an x is constant. So the 12, the derivative of that is 0. Derivative of negative 6x is negative 6. And the derivative of negative 2y is going to be 0, because we pretend like y is constant. It's not going to be negative 2. That'll come later. It's just negative 6. So it's a constant negative 6. That's the derivative of z with respect to x. And hopefully we can see that here. If we sort of ignore the y-axis for a little while and we focus on what's happening exclusively between z and x, that's sort of like this line. And it is a straight line. The slope isn't changing. That's why this function is linear. It makes a plane, not a curvy surface. And it's a constant, the slope is a constant negative 6. So it's steep downwards. Mx is negative 6. And we can do the derivative with respect to y. And that's going to look very similar. 0 here. If we're differentiating with respect to y, this is going to be 0. It's got no y's in it, so it's effectively constant. Derivative of a constant 0. Derivative here will be negative 2. And hopefully we can see that here as well. This is what happens if we sort of ignore the x and look at these things. This is going from 12, very constant straight line, down to 6. So this my is negative 2. On this axis, we decrease at 2 units per y value, and this one we decrease at 6 units per x value. That's partial derivatives. This is a really easy example. Most of the questions in this section are going to be, they're not going to ask you much for geometric interpretations of these things. Mostly they're just going to ask you for finding partial derivatives. And so we're going to do more of that. Some of this stuff gets a little weird. Just wanted to start with that one because that's like the one thing I can draw in 3 dimensions, and you can, if you draw it well, you can kind of see where the different slopes are coming from and what they mean. So let's make up a more interesting problem. Let's do z equals x to the 4th minus 8x squared y cubed plus 16y to the 4th minus the sine of x. I have no idea what this looks like or what it means. I just made it up. It's probably going to be pretty weird looking. Let's see. I don't need to know what it looks like to find a derivative. I can find the derivative of z is, or derivative of z with respect to x. Let's do that one first. 4x cubed is the derivative of this with respect to x. In this one, I get to treat this y like it's a constant, which in this case basically means that I pretend it's part of the coefficient. Coefficients are safe, so it's just going to hang out. Nothing's going to change about this y cubed because it's sort of attached here. Derivative of negative 8x squared should be negative 16x. This is still here. It's part of the coefficient. It's safe. We'll leave that guy alone. This is not a coefficient. There's no x's involved. So it's not the coefficient of anything. The derivative with respect to x is nothing. That piece is going to turn into 0 when I take a derivative. And then the derivative of sine of x should be cosine x. And that's it. We're done. This is the partial of z with respect to x. We can also do a partial of z with respect to y. And that is going to be 0 for this first term, because there's no y's here. X is constant, derivative of the constant is 0. Derivative of this piece with respect to y, this is where we're going to pretend that this x is like a coefficient. We're going to leave it alone. It's not going to change. Coefficients are safe. Derivative of negative 8y cubed should give me negative 24y squared. Derivative of this should be 64y cubed. And derivative of sine of x is 0 because there's no y's involved there. So this is a weird looking function. It's half polynomial, half trigonometric, and here are its 2 partial derivatives. Partial with respect to x, partial with respect to y. All the derivative rules still apply, just treat other variables like they're constant. Which sometimes makes them coefficients, like in this term, and it sometimes just makes them constants, like in these terms, and then the derivative becomes 0. Let's do one more example, and then we can start talking about other weird stuff. Let's do z equals, let's see if I can make this really weird. Let's do y sine x plus x sine y minus e to the xy. I think this one will be fun. Yeah, this is going to be a neat one. Okay, let's do delta z delta x. We'll start with this partial with respect to x. In this term, we're going to pretend like y is just a coefficient. It's hanging out. Nothing weird is happening there. So it'll keep hanging out, and the derivative of sine x is cosine x. And then in this piece, the derivative of x is 1, this is going to be like the coefficient. It's safe, it's just hanging out, nothing weird is happening with that. This is going to be a really good time because this is where we need to introduce the chain rule. So, we all know that the derivative of e to something is e to that something. And then we multiply by the derivative of the inside. The derivative of x times y with respect to x should just be y. So this is e to the xy times y. In the same way that if we were doing f of x equals e to the 3x, that derivative would be e to the 3x times 3. The derivative of e to the xy is e to the xy times y. Same thing. Chain rule is still happening here. It's a strange feeling chain rule because there's a lot more letters involved than there used to be. So let's do the derivative of z with respect to y. Derivative of y is going to be 1. Sine of x is going to be the coefficient, so that'll hang out. Here x is going to be like the coefficient, so that's going to hang out, and the sine of y will be, the derivative of that is cosine y. The derivative of e to the xy is still going to be e to the xy times the derivative of the inside, which in this case is just x. There you go. That is how we take derivatives. So we still have a lot to talk about. Don't think we're finished with this. We are finished with this particular video, but I'm gonna start working on part 2 right away. In part 2, we're going to talk about second derivatives. So stay tuned.